Welcome, my friends. Today we will be discussing capability studies. Capability studies help determine how well a process is performing relative to its specified requirements. By process, I mean some kind of repeated procedure, often in an engineering or manufacturing environment that we would like to evaluate to determine if the process is operating as expected. An example might be a company that manufactures an item such as a food or beverage sold in a grocery store. The product might be expected to have some weight, such as 16 ounces, but there might be some acceptable level of variability around that weight. Maybe it's okay to be between 15.9 and 16.1 ounces. Capability studies can help us determine if the product is being produced within the acceptable range of allowable measurements. Let's discuss some of the notation and important terminology related to capability studies. LSL stands for the lower specification limit, and USL stands for the upper specification limit. We desire the process to operate between the lower and upper specification limits. On a graph of the distribution, the mean will be in the center, LSL will typically be below the mean, and USL will typically be above the mean. In an ideal situation, the mean will be centered perfectly in the middle of the LSL and USL, but oftentimes either the LSL or USL will be closer to the mean, perhaps looking something like this. Back to the ideal situation, any value between LSL and USL is acceptable, and any value in the tails is unacceptable. I will be assuming a bell-shaped normal distribution for simplicity here, but the same idea would apply for other distributions. There are two different measurements we use to determine if a process is capable, meaning operating according to specifications. CP is equal to USL minus LSL divided by 6 times the sample standard deviation, and is the capability of the process regardless of the process center. The numerator, USL minus LSL, is the length of the acceptable region, and the denominator is 6 standard deviations, which can be thought of as 3 standard deviations below the mean and 3 standard deviations above the mean. It turns out that there is a more comprehensive measure of process capability than CP, and that is what is called CPK, the Total Process Capability Index. Whereas CP accounts for just process variation, CPK accounts for both process variation and the process mean or center. CPK considers that the LSL and USL might not be perfectly centered around the mean, as we discussed before. To find CPK, you must find the minimum of CPL and CPU. CPL is equal to X bar minus LSL divided by 3 times the sample standard deviation, and is the process capability based on the lower specification limit. And CPU is equal to USL minus X bar divided by 3 times the sample standard deviation, and is the process capability based on the upper specification limit. We use CPK to determine if the process is capable or in control. If CPK is greater than 1.33, the process is said to be capable and functioning properly. No corrective action is needed. If CPK is between 1 and 1.33, the process is capable but should be monitored with tight controls. If CPK is less than 1, the process is incapable and corrective action should be taken. This might amount to adjusting a machine or perhaps instructing employees to change their working procedure in some way to correct the problem. Now, inevitably, in almost every process, there will be some units that fall into the unacceptable range outside of the lower and upper specification limits. Sometimes it's helpful to calculate the parts per million, or ppm, which is the number of units out of 1 million that you might expect to see outside of the specified limits of the process. To do this, we calculate the probability of observing a result in one of the unacceptable regions of the distribution, and multiply by 1 million. To do this, we must calculate z-scores corresponding to the upper and lower specification limits using these formulas. We will talk more in detail about how that procedure works when we look at an example, which we will turn to now. LSL Enterprises produces cartons of orange juice and would like each carton to contain between 59 and 61 ounces of orange juice. A sample of 50 cartons revealed a mean of 60.3 ounces and a standard deviation of 0.4 ounces. Assuming the population is normally distributed, calculate CP, CPK, and ppm. Let's start by listing out some of the given information. The lower and upper specification limits are 59 and 61. This is the range of acceptable ounces for each carton of orange juice. The sample mean, x bar, is 60.3, and the sample standard deviation, s, is 0.4. The sample size is 50, but I'm not going to list that out, as it's not used in any of our calculations. Drawing the graph of the distribution, we see that the mean of 60.3 is slightly closer to the upper specification limit of 61 than it is to the lower specification limit of 59. Let's move to calculating CP, which is equal to USL minus LSL divided by 6 times the standard deviation. 61 minus 59 divided by 6 times 0.4 is equal to 2 divided by 2.4, or about 0.83. This is the capability measure assuming the mean is in the middle of the two specification limits. But, of course, it isn't in this example. This value only takes into consideration the variability of the process and not the center. To consider the center and the variability, we turn to CPK, which is the minimum of CPL or CPU. CPL is x bar minus LSL divided by 3s, and is equal to 60.3 minus 59 divided by 3 times 0.4, which simplifies to about 1.08. CPU is USL minus x bar divided by 3s, and is equal to 61 minus 60.3 divided by 3 times 0.4, and simplifies to about 0.58. The smaller of these two values is 0.58 and becomes our CPK, the Total Process Capability Index. According to our criteria discussed from before, our value of 0.58 is less than 1 and is incapable or out of control and requires corrective action. It appears our process is not centered around 60 as it should be for it to be in the middle of the specification limits, and the variability is high enough that many of the cartons will be produced outside of the lower and upper specification limits. But exactly how many will there be? To answer that question, we turn to the parts per million, which involves finding the probability of observing a result in either tail of the distribution, outside of the specification limits, and then multiplying by 1 million. To do this, we need to find the z-scores corresponding to the upper and lower specification limits, using these two formulas. The lower z-score is 59 minus 60.3 divided by 0.4, and is equal to negative 3.25. The upper z-score is 61 minus 60.3 divided by 0.4, which is equal to 1.75. Let's look up each of these values in a z-table to find the corresponding probabilities. The table I'm using calculates the probability from the center up to the desired z-score. In the z-table, we can see the probability associated with 1.75 is 0.4599, and the probability associated with negative 3.25 is 0.4994. Since the distribution is symmetrical, we can look up positive 3.25 instead of negative 3.25 and still get the correct probability. The probabilities I found can be included in the graph. They are the area up to or down to the corresponding specification limit. In order to find the tail area, the probability of observing an outcome outside of the specification limits, we take 0.5 and subtract each probability, as the area above or below the mean of a normal distribution is 0.5. 0.5 minus 0.4994 equals 0.0006, and 0.5 minus 0.4599 equals 0.0401. These are the two tail areas, which also can be included in the graph. Adding these two probabilities together, we have 0.0006 plus 0.0401, which equals 0.0407. To find the parts per million, we multiply by 1 million. 0.0407 times 1 million is 40,700. So about 40,700 cartons of orange juice out of 1 million will fall into the unacceptable zone, either above the upper specification limit or below the lower specification limit. It would be up to management to decide if this number is acceptable, but my guess is that might be too many units outside of the acceptable range. Alright my friends, that wraps up our discussion of capability studies. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.